So I'm very honored to be able to present to you the CEDA Technical Distinguished Lecture today. Our lecturer is on the screen up there, David Culler from UC Berkeley. He biked here, I think, which explains why he was a little late. Wolf would have ran here. If Wolf was coming, he would have probably taken a run over here. These people who are sort of actors, they like doing that.
Okay, so I guess I get to play the local host or something, being from a small public school across the bay there. Talk to a few of you from the East Coast and the Northeast and whatnot, that the sun actually shines in California. So I hope you're enjoying yourself, and I appreciate that you take a few minutes and come join me rather than exploring the wonders of San Francisco. So I guess my job is to entertain you for a little bit, and we have a really nice hot mic up here. Internet of Things. I heard from our AV that was all over CBS this morning. It's all the rage, it's all the hype. So I thought I would do just kind of an amusing perspective on these last 15 years or so. So Back to the Future. So what I thought I'd do, first spend a moment looking back. Sort of what were those decade of results that actually made a difference coming out of the research community? And it's rare that we have such an opportunity when it's all the rage all around us to say, well, actually, we had a lot to do with that. So I'll try to pull some of those pieces off. A little interlude. I'm thrilled, yes, for the service of humanity. So I'll take a slide to interlude on my little tour into sustainability before returning back. And I've included, although I guess you can't quite see it there, an old slide on kind of the tides of innovation. That, everything in the fields we live in is a straight line on a semi-log plot. That's nice. What that's partly getting at is the tremendous power of innovation. And in fact, when the new generation arrives, it's not because the old generation is struggling. Generally, it's at the height of its dominance. And what used to be hard has become easy, and what used to be impossible has become tractable. So it's obviously a question. We think we're always in one of those steep upturns, and perhaps we are, or perhaps we're about to see what replaces the incredible run that the mobile phone has. So back in 1999, we said in 15 years, we'll have connected essentially all the people on the planet and have the technology connect everything. So November 2014, we hit 3 billion people, 40% of the world's population. So pretty good guess. Some of that was driven just by the underlying economics of how these things change. And this is looking in very crude terms at the cost to connect. That as these things fall, the transition is from connecting computers, machines, connecting people, to connecting things. And of course, the other side of that is the nature of what you do really changes from sharing information really to creating awareness. And that's beginning. And if you don't believe me, and it's all hand waving, I had to go grab some slides from my colleague Randy Katz of the Endeavor. Many of you in this room may have been part of those DARPA expeditions to the 21st century, Endeavor at Berkeley, and Oxygen at MIT, and Aurora at CMU, and a couple more. And we really did understand back then that we would be blowing the computer apart and spreading it into our environment, and that it would be reaching all the way down to devices essentially embedded everywhere in these information utilities. So, we even have slideware at least, which is to say that the things we fantasized about that were so amazing are now realizable. And it's an exciting time to be living in. Okay, so 99, the web looked like this, literally. That picture's from 99. Connecting all the devices. Of course, by then, massive search had arrived. We had more and more computing in the core of it. Remember, the Palm Pilot broke on the scene. It was going to be, the connectivity was not great. There was sort of a serial port and an ERDA on the side. Gee, I can barely see that. That's your ricochet modem we all had attached to the back of our, from Metrocom and whatnot. And that's actually the PDQ Qualcomm, the first smartphone, a Palm Pilot and a cell phone. You can barely stick it if you've got a really big, I mean, it would make Maxwell Smart really happy to carry a thing like that. Okay, so that was what the internet looked like. What the internet we envisioned was really a very different place, in that it really had to do with connecting all of these sources of physical information, connecting to the physical world. And, you know, why is, and we have to coin a phrase, you know, that we lived for decades, maybe millennia, in human-generated information. We now live in the world of non-human generated, non-human generated information. But, you know, the applications of this technology really are so foundational. They're so far beyond entertainment and whatnot. They have to do with real productivity. They have to do with safe food and water. They have to do with infrastructures that are energy efficient and conducive. They have to do with logistics and health. And in fact, what I found in my own life is the sheer importance of the applications. It's its own kind of friction, because these things really do deal with so many parts of life. Part of what made this journey so interesting was that it wasn't really high-tech like most of the transformations we talk about. I mean, basically the microcontrollers that were all the rage were, you know, the stuff in your toasters, storage from your thumb drives. You know, the radios were essentially key fobs and controllers for your PlayStation. You know, of course, what was interesting was that sensors, all of a sudden, instead of being gadgets, they too became integrated. So, you know, what happened was the computing, the storage, the connectivity, all of that went into the devices we deploy in the world, and increasingly the only thing that came out was the network. So, 2007, you'd have to say the Internet of Everybody arrived, right? That, you know, at that point, this whole new tier emerged. Not just your iPhone and the Wii, but connecting to all of the other sorts of activities we did. And roll forward to 2013, you know, oh my gosh, October 2012, the internet light bulb finally emerged, you know, starting from 10 years earlier with Zigbee. And of course, the Nest thermostat was all the rage. And you know, what happened? Well, essentially, every piece of light moved over to LEDs, and therefore it's modulated, and therefore you have to have electronics. If you're going to go through all of that, you might as well put a network inside of it. And all. So lighting is transformed, and of course, the bottom fell out of the network thermostat market almost immediately. Everybody has 17 on the market. You know, and CES, it was the year of the wearables, all of that stuff we're carrying around us. So also notice the communities of what's connected over Wi-Fi, over low pan, over Bluetooth low energy, that it's this fractioned world. Okay, so that's one take through. When we looked at this back in 1999, what was the perspective of many of us, you know, driving into the embedded wireless network world? Well, number one was we would have to give up the internet architecture. All of the tenets of that, layering itself. We would have to eschew layering, the thing that had given us the power to grow in these unprecedented ways. The sheer numbers, and in particular, and this is one that's still the challenge of unattended deployment, cause us to completely rethink how we manage and deploy these. That we'll start pushing algorithms down inside the network rather than at the endpoints. We won't even need an address anymore. IP addresses will fade. And in fact, there won't be a generic protocol. We'll build networking protocols for each and every application. Fortunately, we were wrong. But the sheer opportunity to set all those architectural constraints aside meant that the research community, in some sense, had open license to just go tackle problems any way they could. And, you know, of course, it created an incredible chaos. And it was interesting after many of those, and I'll say a few more words about them, that then it became possible, and I guess what did Moore say? Let chaos reign, and then reign in the chaos. So in 2008, that exercise to say, okay, what if we now take everything we learned from the research community and apply it back to the internet architecture? Can you do it? So 2008, IP over 15.4 realized on devices that, you know, carried, what, 24 kilobytes of ROM and 4 kilobytes of RAM. And, you know, there you see over there the breakdown of each and every piece all the way up to the TCP IP stack, and you could even put a web server on you like it. Okay. This was the industrial implementation, the open source implementation, about 10% bigger. It seemed like we had really created the internet of everything. It was here. I then spent 4 years traveling to far too many IETF meetings. In 2 years, we actually had a standard, Ripple, routing over low power and lossy networks, hammering that out in the strange, rough consensus that these things emerged. It seemed like the world was going to change. Okay, so what did it take to get there? And part of this exercise was it was this fabulous global open source hardware and open source software. And it's tough to boil it down, but I'd boil it down to 4 major research contributions. One was really a truly event-driven component-based operating system. Treat software like hardware so that you can really assemble the building blocks to very efficient but also highly tailored applications out of common stuff. Number 2, we all talk about computation and transmission and all of that baloney. If you're talking low power, all of the energy goes into doing nothing. We tend to do nothing incredibly poorly. The key was to do nothing well. Talk a little bit more about that. In particular, how do you turn your radio on only when there's something to hear? How do you turn your sensor on only when there's something to sense? How do you know? This is the world we live in. It is insane that you have to babysit your cell phone and charge the poor thing every day. It's got this immense battery. You have to go, you're spending your life running around babysitting your electronic devices. No, in an unattended world, different world. Obviously, routing over these really yucky networks that are continually changing out from under you. And what is so interesting, if you think about routing over space, you think about communication, and very far you got none, very close, it's great. Right in between, it's really noisy, and that's always where you're functioning. Because any less than that, you took too short a hop, any larger, you... So this dealing with uncertainty is really fundamental in routing. And the last one is that embedded networking has to be polite. All of us start out writing flooding protocols. No, you never flood. You trickle. You never broadcast. You always listen before you speak. And then you speak very gently, and you pay attention to how many others are in the room, and you only take your share of the conversation. Okay, let me say a few more words about each of these things. But the real message, if you take nothing else away from any of this, your talk about humanity, think about transportation for a second. This is doing nothing pretty well. This is doing nothing not so well. This is doing nothing really poorly. Okay? Today, all of your servers consume, well, now we're getting down to only 35% of peak power when totally idle. Right? If your car was spinning its wheels in the drive, even your cell phone is still a significant, measured in tens, not ones of percentages. Okay, so one piece of this, purely from a hardware point of view, was this fascinating interplay of hardware, software, research, government, industry over a 15-year period, starting with early investments largely from DARPA. And there really were two communities from the very beginning. Those on the top that were essentially trying to push Linux boxes down, which were a cubic foot at the time, and those that were taking key fobs and things and trying to push them up. The kind of starting point of an architecture, we called it Rene because it was Cartesian, really launched at a point where we suddenly had 8 kilobytes of ROM and half a kilobyte of RAM. Oh my gosh, we could program, we could build an operating system. That gave rise into the DARPA NEST program, which involved contractors throughout the country building on a common platform and 3 generations over 4 years of platform. Enter in various big players like Intel and so forth. And let me say, at this point, nobody believed you could put Wi-Fi on a single chip. It was a 4-chip solution. Bluetooth was here. IBM was going to deliver it to me in 1998. It was telecom through and through. A minute was a perfectly reasonable time to establish a connection. So the world was really very confused. Okay, NSF enters into the game. Big efforts, for example, with Intel, Bluetooth starts to ship in the millions. Surely that's the path, which merely proved out from a protocol point of view, if I have to establish a connection before I can communicate, I really cannot build networks out of it. Okay, we'll see that all changed. Motorola, other players. In 2003-04, really this tremendous transformation where 15.4 became a standard. All sorts of companies started producing it. At the same time, we had a new class of device with things like the CC2420 and the MSP430, where you had 64 kilobytes of RAM. We could actually get rolling. 48 with 10 kilobytes of RAM. 15.4. It seemed like this was the breakthrough, and indeed, then all sorts of development starts to grow around that. We built networks in the thousands. Now, rolling forward, we see the iPhone and whatnot come to exist. We see CMOS 802.11. We see that reducing down into the corner. We see consolidation within the research community and so forth. And a point in 2008 where we've got an IETF standard as well. Okay? And these kind of wrinkles of this thing called WIBRI, of beginning to go back and rethink Bluetooth as something that might be a networking primitive. Okay. On the operating system side, fascinating experience to really drive this open source worldwide community. And one way of looking at it is an operating system in this space has the same kind of building blocks as you would expect in any other. That you've got the networking subsystem, you've got storage, you have scheduling and processing, and you have sensors where you would have normal I/O. So this is my one slide of what does it take to build systems in this space? Well, okay, it starts with the sensor, which means information is now streaming in. Of course, the power is that you can do processing at the sensor. So you can transform that information into something more interesting. You can do all sorts of things with it. For example, you could store it, you could start to accumulate things. That means you can do analysis, you can do learning, you can do smoothing, you can see trends. But of course, what's also wonderful is you can transmit that, so you can do something with it. You connect it to the rest of the world. You can make this the back end. Even more powerful is that you have a network of these, and so you're collecting information from other devices in the space. And so if you were to look at it in a snapshot, this is what it looks like. In other words, you're teaching systems how to juggle. And from a design point of view, is how do you keep a large number of concurrent flows in a very small footprint and do that in a way that maintain the structure? The kind of things that you might synthesize. And in fact, the very first form of TinyOS, it was actually VHDL as a orchestration language. It was structural VHDL. Okay, it evolved from that. So, the world of where this community is and where that began were very close. Treat software like hardware. Okay, but communication-centric, resource-constrained, event-driven execution. And some really interesting aspects of what the interfaces look like. In particular, this notion of bidirectional interfaces, so you can do interpositioning, which we always do in hardware, and in software, we almost always leave behind. Okay. So, and it was really Deborah Estrin that coined the term. She started focused on the Wi-Fi side. And the bottom line, when you look at low-power wireless, is the power consumption is essentially the same whenever it's on, no matter what it's doing. If you're transmitting, if you're receiving, if you just have your radio on, waiting to hear something, it's roughly the same. You're no longer dominated by the amplifiers. So what that says is, since you've got to have it on in order to hear anything, how do you turn it on? Only when there's something to hear, okay? So if you went back and looked at where the energy went, the answer was all of it went to just sitting there listening, hearing nothing. Okay, so to drive that home, let's make sure we've got this. Here's a picture, time going across. You sleep at a few microamps, you transmit at maybe tens of milliamps. The notion is, I'm motoring along, I'm asleep, I'm in idle. You can transmit all you like. Okay, it costs you something. Transmit all you'd like. If I don't turn my receiver on, I don't hear you. Talk's cheap, listening's hard. Okay, so the whole point is I've got to have it on when you get around to transmitting, and then I'll receive it. And from a power point of view, I can hardly tell. So the whole question is, how is it that I turn it on just when there's something to hear? That was the idle listening problem. There are basically three solutions to this. There's the one that is typical of electrical engineers, which is the TDMA solution, or more generally, scheduled listening. If we want to meet, let's arrange a time. And we arrange the schedule, and you know what? It's great if we do it lots, and it's a really pain to set it up. And every time something goes wrong, there's a great cost in reestablishing the coordination, which we tend. Then there's the typical computer science approach, which would be CSMA. And this you can also think of like peripheral vision. What you do is you turn it on for just a little bit to hear, might there be something out there? And what we're really doing is we're shifting the cost of reception over to transmission, which is rare. So what's going to happen is on the receiver, I'm going to turn it on just a tiny bit. Is there any energy? Oh my gosh, there's energy. Let me see if I can grab a packet, otherwise I'll go to sleep. And in exchange for that, I'll make the transmission long enough that it crosses the interval between those teeny tiny peaks. Okay, there's the other one that we used ever since modems were invented, and probably smoke signals, which is listen after send. If I've talked to you, you might have something to say to me, so maybe I should keep my receiver on. The interesting thing is all hybrids of this are interesting and possible, and there's a zillion papers to publish there. So 15.4E and G actually did the work that was missing in 15.4 to address the idle listening problem. In fact, some of you might ask, which one did they choose? The answer was D, all of the above. So and unfortunately there's a big switch that says which one you're doing when there's these really beautiful ways they could have been implemented. So it's in the standard now. Interestingly, it has made it into Ethernet. So if you look at energy efficient Ethernet, it's doing low power listening. But it hasn't made it into Wi-Fi. Why not? AMAT never did work, so there's all this opportunity, all these non-proprietary. Okay. The other, of course, was self-organized routing. And concept here, very simple. I have all these devices spread over space. And unlike your access point, they are where they want to be, not where communication is convenient. And I don't know advance, but if I've transmitted, then there's some nodes that heard me. Some of them I can hear, so they could think of themselves as the next tier, if you will. And if they were to retransmit, then I can start to build this graph. And if I repeat that process, then I can find the connectivity between things by using them, routing around obstacles, because if I didn't hear you, it wasn't there and whatnot. And if I have something to say, then I can just reverse that path. I always love the term multi-hop routing. If routing, it better be multi-hop. I mean, so that, of course, everything I said to you was a lie. Because all of these algorithms that build a tree and reverse the edge don't work. They're all incredibly brittle. This was true of several of the early ZigBee and many of the naive implementations and many of, so the key, in addition to coding diversity, temporal diversity, retransmission, and symbol frequency diversity, you need routing diversity. At every hop, you have to be prepared to take an alternative path. You need to maintain a small number of choices. If you're driving this evening around San Francisco, always maintain 1 or 2 degrees of freedom. You don't need n, you need 1 or 2. So routing diversity. This did make it into Ripple. The second was your rate of, you never retransmit because you heard something, that your rate of retransmission must be a function of the density around you. So that, if you will, the flux of communication over space is constant, independent of the density of devices. That's trickle, and that also made it into the spec. Okay. The other thing that made it seem like the world is ready to change was IPv6 was designed for the Internet of Everything. Huge addresses, automatic management, integrated bootstrap and discovery. The option framework was beautiful. There's some other things like assuming gigabit links and whatnot that were part of it. Okay, so there were some little challenges, like the minimum MTU in 15.4 is 1,040 bytes, and the maximum in a 15.4 frame is 256. Oh, okay, that's a little bit of a problem. You had other issues that if you're carrying around a bunch of 128-bit addresses, they don't exactly fit in a little package. So this was what the low-pan adaptation layer did. I call it the Humpty Dumpty approach to network protocols, in that what you basically did was everything you could derive from the low-level information at the wire, you would elide at the high level. So you break all the layers of abstraction, and then you kind of put them all back together again. So this was a nice piece of work that basically made, okay, you could carry IPv6 over 15.4. Okay. 2008, the standard is done, the research has been done, the world has changed. We're off deploying electric meters in the millions. I thought embedded wireless networking was done. And personally, I was much more focused on this technology has tremendous value to the world. Go do that. I'm so happy to hear CEDA's charge, go do that. So automated meter reading. I engaged on a little project. If you were designing the electric grid after the internet, how would you think about that? Distributed generation, fluctuating non-dispatchable renewables. How do we create dispatchable demand? How do we turn this into a network? How do we take all of that different kinds of physical information, all of the ISOs, the weather, the electrical, what you're doing, bring it together so that you could begin to program the infrastructure. Got farther into building operating systems. I mean operating systems for buildings, because it's not just an app on your phone. I should walk into this building and acquire apps for the Moscone Center. For God's sake, just finding your way around is enough of a challenge. So many places where this technology can be brought to bear. Do more of that. Oh, yeah, we're doing microsynchrophasers. So there's about 1,000 now distributed through the transmission tier. So this is a couple hundred hertz sampling on a dozen channels, synchronized down to a few nanoseconds, collect all of that. Finally, sensors that actually generate some data. We got terabytes of the stuff, you know, it gets interesting. So it was a great interlude. All of those wireless networks and lighters, we built Open Bass, which was a horizontal integration of all of those vertically integrated stovepipes and the rest of that garbage so that I could actually program up my building and all the rest of it. Okay, that brought us, for me, to the day. And so what happened? It seemed like 2008, by now, the Internet of Things would be everywhere. Okay, well, basically, wireless embedded networks are the same place they were in 2008. Ripple did not take over the world. Its flaws probably will prevent it from ever so. Zigbee didn't either. It became a compliance organization from Ripple, which didn't take over the world. And the research community is elsewhere. The principles remain. The importance of it's so fascinating, the Internet of Things with no internet on it. Of course, you know, the smartphone continues its amazing trajectory, and I refer to it as not a triple point but a quad point, in that it ties together the human, everything out there on the internet, the physical space around you with its sensors and cameras and whatnot, and the digital space around you with its short-range networks. Then, of course, there was the maker revolution. Everybody building this god-awful stuff, slapping it together. So exciting. And all of the wearables. And who talks to whom here? Well, for each wearable, you can get an app on your phone that will talk to it over a glorified wireless USB called BLE. So the future seems very obvious from here in that there's this opportunity to bring these together, that most of what we're thinking about here has to do now with this synergy of that we carry, that what we move through, and all of these different. So a year ago, we actually built a new Mote. And this was interesting because it took 3 generations of the ARM Cortex, and I expected it. And we had those conversations before that magical, what did I say? Do nothing well. Idle current below 10 microwatts. Okay? Finally, it arrived. We happened to be using the Cortex M4 with BLE and whatnot. So one of my students just couldn't help himself, so we built a new module. We called it Storm, which, and we build these motes essentially on a fancy board that allows them to function like chips, so you can drop them on a carrier that anybody in the world could design with Eagle, so we can go have fun with it. So the key was, finally, after 17 years, we have a 32-bit microprocessor with all the peripherals. The ARM thumb in 1999 did it, but it didn't give you anything of the rest, with a fast wake-up and a low idle power. Okay, so does this matter? This does matter. The other reason why, as much as we had an implementation of IPv6 on those little dorky devices, there was no room for anything else. So it wasn't really all that useful. We dropped that on a carrier board. If you were going to drop it onto a carrier board and you were maybe offering a course, you'd put it on an Arduino compatible board. So we did. That's going to bring in all of the maker stuff, except for the software in the maker world, which, let me tell you, that is so wonderful, because the software that's out there is so awful and difficult to use. So it was great that we had no software compatibility. There's a lot. So those two. Of course, we dropped BLE onto it. BLE still functions thinking the world is made up of central and peripheral, client and server. It's peripheral heritage. We can talk to both, which means these devices could talk to you through your phone. That's huge. Or they could talk to tags in the environment. God's sake that the tags have folks they need to talk to besides. So this is a pretty interesting platform all by itself. If you think about performance, lifetime, and connectivity, then it's at a very different place than where we've been able to be before. This is to say, if you were doing software synthesis for embedded devices, for network embedded devices, it would be so much better than it ever has been. There's a zillion things. The nasty thing about doing nothing well is you have to pay attention to everything, because the last little thing that you're never doing will bite you too. This was examples of things like, it was a bummer for a decade that the flash required a higher supply voltage than the rest of the chips. So you had a bug, but you couldn't do it because your battery was depleted and you couldn't so there's a kind of universality that kicks in. This is a picture to say this is a world where you're dealing with 5 orders of magnitude dynamic range. Okay? The vast majority of the time you're down there at 3 microamps, and when you're doing anything you're at 30 milliamps. Okay? And that you have to look at it that way. So the other piece was we had sort of moved to this world of 3 Ps. And I think we're good time-wise? Right, good. So the other question is, does it begin to open up the software world in interesting ways? So where I had been with TinyOS, what drove that was treat software like hardware. Application-specific assembly of a variety of well-developed components, and this structured event-driven execution model. And in particular, it wasn't one source fits all. You ought to build a system for a purpose. Okay, so the other thing we have today is we're back to the 60s. We have user and kernel on embedded devices. We have a protection boundary. Okay, so we took everything we had done in the TinyOS space and lifted it up to a really interesting asynchronous syscall interface. As soon as you do that, you can put libc on top of it. When you can put libc on top of it, you can put anything on top of it. Lua is an embedded scripting language. That sounds like a great thing. It actually was pretty cool. All of a sudden now, embedded programming is easier than scripting on the web. You can jump in and start building things right away, and then you can start pushing things down. In particular, Lua also has this notion that you can take things from this high-level scripting environment and you can encapsulate them in C. So the things that you care about, the signal processing and so forth, and if you really were serious, you could push it down into the kernel. Okay, so what's the litmus test of any good system? The answer would be teaching a course on it. So last semester I got to do my Internet of Everyday Things studio, and I thought, as dessert, I would just share a little bit of that. So I had once taught this before in 2008, and the idea here, there's no lectures, we live in the lab, and we say, you look at all of those appliances, bring them in, we're going to tear them apart. We're going to put computing and communications in, we'll put them back together, they might work, and then we're going to build really interesting applications out of ensembles of them. Okay? So I thought I'd spend 5 or 6 minutes and just tell you what my last semester was like, give you a sense of it. I guess you can see a little bit. Basically what happens in this world is you connect your Firestorm and you open up a shell onto your device. which means you can toggle pins at the command line. Okay, that's a starting point. You could start to script and build the things you think about as an embedded device, and then you grow and you start programming it. Okay, so what do you need to learn? You need to learn about time, you need to learn about state, you need to learn about how to generate waveforms. This is what's underneath all of that. And so you write tiny little bits of code, I realize you can't read it, that toggle pins, and all of a sudden you do beautiful things like you encapsulate the state in a closure. And so a lot of the things that in state machines were yucky become beautiful. And, you know, go build your blinker. So on the hardware side, of course, you have all these starter shields and things, you know. So the same day you write some of this code and you get out a soldering iron, you know, students these days don't even know which end to use, but they learn after a little bit. This was also an excursion in how do you do design for event-driven concurrency. And there was another innovation that came out originally from C# and then into JavaScript through Node and whatnot, which was await. So I won't do a lot of it, but it basically is this beautiful notion that if you're consistent about an asynchronous call taking the callback as the last parameter, then these complicated state machines can be really elegant to write. This, you can't quite read it. I'm sure back there was an example of a piece of code that's flashing an LED, and instead of invoking something at some period of time, you can simply await time to go by. This is, again, doing nothing well, servicing lots of other things or going to sleep, and it looks like sequential code. Big, complicated initializations with long latency things became simple. I was a convert. Okay, what's the pace of this? Week 1, you build an embedded thing. It's got buttons and lights, and you did whack-a-mole and whatnot. Week 2, you build a network thing. You got buttons on one thing and lights over there, they real robots and things. You could really get turnaround on that basis. Week 3, we had designed our discovery protocol. They walked into class, everybody's implementing their piece of the protocol. The sniffer you can see on the screen, you see the malformed packets, you see one group has figured out, the light over there goes on, you start to see the whole service discovery and application come together. Okay, so we broke toasters open, alarms, finger painting, all of that. Okay, so, you know, this is what it looked like inside a class. It was so much fun. It made a real mess. People tearing things apart. Okay, so, you know, and then you get into this whole dual stack of course, it's Bluetooth and it's IP over LowPan, and you connect the world around and the outside. And and by the way, you learn about memory mapped I/O and ADCs and all of the rest of those kind of things. And then you were ready to hack your appliance. Okay, so here's an example. Here's a fan. You crack it open, you put a few relays and a device on the side of it. You can see that on the side. And all of a sudden you can walk up to it with your phone and it discovers that it's a fan and it gets an interface to it and you can interact with the fan, and oh, by the way, you can record all of that in the background, and you can't read it there, but it's literally a screen of code to build the whole application. You could do things like grab an Ether shield off the shelf and build an IP router to go from Ethernet to LowPan and whatnot. You didn't have to throw a Linux box into the picture. Oh, and by the way, you could walk up to that dorky embedded router with your phone and you had a console interface to it over Bluetooth. I mean, this stuff starts to make sense. Okay, so this was a piece we did to then kind of grow this discovery protocol in an inclusive California, Berkeley-like world. So there's all of this Bluetooth profiles that nobody follows and whatnot. So what we did was, if you had a device and you're advertising your services over Bluetooth, you advertise them over LowPan as well, over IP. And of course, the Bluetooth profile didn't describe the actual service. So what do? Well, the real manifest lives in GitHub. You have a new product. You have to get a new number for your profile. You don't go to IANA or the equivalent. You do a pull request on GitHub and it gives you a device. So the whole class starts building devices and pushing them out there. This means a phone that walks up and discovers a bunch of devices does not have to have the application on it for the device. The device says, I'm a networked fan, and the phone says, I never met a networked fan, but I have your ID. I can get the rest of it. I can build an app. I can do that. So you could start to just put these worlds together. What this is showing is it doesn't start, that the fan recruits the thermostat from some other part of the room. Now I have a control loop, that's called HVAC, on the fly. You can actually just start building ensembles of devices for a purpose. Okay, so, the midterm, we're looking like this. I thought what I'd do is I'd show you the final projects. Okay, so, here the students are running around. You can see some of them have a rice cooker they're taking apart. We're getting ready for the final project. Here's what some of them looked like. You have your story on your iPad. Okay, 3 little pigs. You walk into a room. He huffs and he puffs and the fan comes on. Okay, and I'll burn the house down and the heater comes on. So, you remember earthquakes surround around. You're recruiting things. If you think about it, it's very interesting. How did you find what could do what? Okay. These guys scripted the kitchen. So you've got several appliances. Of course, each one of them are programmable. The recipe ought to be a script, but more important, the menu ought to coordinate the recipes. The devices should help you remember, hey, start me over here or the rice won't be done on time. Okay, so they could assist you in putting it together. Another group wanted to see how much could you do with a rice cooker. And, it's only got one heating element, so they just, okay. Another group, the world needs to express itself. So forget Chromecast, although that's where they started, was just ambient displays. And think about what you might use them for. Sure, you walk in and it says, hey, hi, David, you forgot to lock your bike. There's all of those kind of, the things in the room gain a way to talk to you. So it was really important that these become part of it. So all sorts of projects began using the ambient displays, and this was the point, was it's not just build a thing, build an ensemble of things built out of things that you didn't build. So for example, these folks took your magnetic read sensor, you could put it on a box. Okay, fine, it's not an alarm system. Your jewelry box is really one kind of thing, or nobody's supposed to open that when you're away, versus the medicine cabinet, which is supposed to be opened ever so often. And you could imagine that those are networked. They could talk to you on your phone. You ignore your phone, but they could show up on the display, hey, So that was an example. These folks got going on, I work with the Center for Built Environment to do personalized environmental control. So what you can't see very well is the chair underneath it. So let me tell you about this chair. Okay. For starters, think about your office. Lots of people, lots of cubes. What's it controlled by? Well, the thermostat. There's, 2 of them in some bizarre corners over there. You didn't want to set the temperature. Here's what you really wanted. You wanted a comfort dial. Now, if you had a comfort dial, we could ask, what would you set that to? Probably 11, right? But is it hot, cold, your comfort different than my comfort, your view? Okay, so what's about this chair is it's got heating and cooling built into it. And you can do this in about 5 watts. You actually don't need much thermodynamic transfer. If you think about where those heating elements and cooling elements are, you're very sensitive there. You're actually very sensitive to if your ankles are warm, you're warm, if your face is a little cool. It's not about your temperature. You're designed to live outdoors. It's about your perception of comfort. But imagine a room full of these chairs. If on average, nobody has them on, everybody's comfortable. Right? So a network of these chairs give you information that's very different than what you get from any one. Okay. Other groups started to do with lighting. Not just your emergency lighting on the airplane, but You wake up at night, maybe you're older, maybe you're going downhill in terms of dementia or whatnot. Can the lights help you find the restroom? Right? What are the different ways that they could come together? These folks started near and dear to your hearts here. I walk into a room, I want to build an app for this room on my phone. It should discover the devices and give me graphical programming to script an application, and then I should be able to deposit it in the room and walk away. Interesting question. These guys put 4 sensors into the medicine cabinet, integrated with the display. You're supposed to take your pill. I know you only took one today. Active networks, we started getting back into doing network evaluation, and by the answer, it's terrible. Okay, so I'm going to skip what happened down inside there. So where is this all going? Well, it's a pretty cluttered picture. Greg Papadopoulos once told me the best networks are uninteresting because they work. That's really our goal. So in some sense, wireless networks, embedded wireless networks, are getting uninteresting too. And that's our goal, make them uninteresting. But it's really about ensembles. So what you're trying to get out of this picture is you will carry a personal environment. That personal environment will walk into your home environment, your work environment, your physical environment. Your car is a network of things as well. Those are 3 networks you interact with. Those 3 networks are also interacting with the social infrastructure, the grid. I want to charge my car based on availability. All of those have a lot to do with your social networks. My willingness to ride or walk from here to work may have a lot to do with other friends riding or walking. So where this is going is ensembles, not just of devices, but of networks that are often put together based on some larger goal. Thanks.
Thanks very much, David. I think we have time for a couple of questions, but before that, I wanted to give you this nice souvenir for your desk from CEDA.
Thank you.
There's a microphone in the middle of the room. I'm sure many of you have many questions that you would like to ask David. I'm going to start with one that I was intrigued by all of that. So all of this adaptive software that it's going to be written, I imagine there's a lot of room for maliciousness in that sense.
Yeah, yeah.
One might make my chair heat up instead of cool down or whatever. What's built into the system to prevent hackers or whatever?
Yeah, or maybe the question is what should be built into the system. So a lot of what we did in the class, the answer was next to nothing. That's not to say that's the right thing, that it's the, you're exploring ideas. This is a huge open area. Some of the pieces that we built in here, one of the things, encryption devices now are IP on almost everything. So one of the things we did in the system was to make it so easy that absolutely anything you could do, you could slap AES on top of it. And we actually have built up this apparatus around it that provides a kind of delegation of trust. That's still early. We're still working through that. It's a pretty interesting thing. It comes back to the power of connectivity. So a form of it is, it's a scripting relationship to say this light switch is publishing to that light bulb. This light bulb is subscribing to this light switch. Okay. How did that relationship get established? The act of forming the binding needs to refer back to the building was owned by the chancellor, if you will, who delegated to the facility manager, who delegated to you, and that you do have the right, if you will, to drop an application into your office. So it's an area where there's a huge open space to deal with. Part of what we find is that your normal intuition about computer security doesn't carry over. Okay? So for example, we did personalized lighting control. Anybody walk into a space on their cell phone, they grab access to the lights. But it's a group activity, so one of the principles was don't resolve human conflict by technical means. Good advice. So, the issue here was how do you get access? So we decided there we would use the campus-wide authentication system. So anybody that had a campus ID could have access to the lights. For God's sake, when you walk over the light switch, you expect to be able to turn it on. Okay? That was a trade-off of, visitors versus occupants. The interesting thing was the social etiquette that developed around it. It was, you actually will converge to whoever likes it lightest. Okay? That wasn't a technical factor, it was how people chose to use it. Whereas when we did personalized HVAC, we threw in a voting structure. So you had to get somebody else to kind of agree with you. So it's not just security, it's also privacy, and it's human protocol that kind of have to go together for these applications to work sort of naturally. Long answer to short question, great question. Other questions?
I know we're kind of running out of time. Any last questions before we thank the speaker again? Everybody's itching. David? There's a mic back there, but you have a loud voice.
Yeah. I'll repeat it.
Thank you very much for the talk. Actually, it was interesting to notice that most of the innovation that you presented has been mainly on the networks. You also outlined a little bit that was a big thing to be done, which is you want to be idle and not representative.
Okay.
When you presented, you have already commerced an arm, a cortex, and so on. There's nothing else to be done there. Do you think there's still a lot of things that we can actually enable to go in the direction? There's a lot of things needed to really make these devices work forever, like energy scavenger, whatever you see.
Yeah. So I think the question was, are there things at the hardware level left to do for low power? It seems to be on the networking side. And first I want to respond a little bit to the question. The hardware can only give you the potential to do it. Every other layer has the potential to screw it up and generally does. So that's the most important one there. There's a tremendous amount of space to continue to innovate. So in order to get a Arduino-like thing to actually obey the 10 microwatt lifetime requirement, you had to extend the programmable clock domains into all of these other devices where it didn't go. Okay? These notions of passive vigilance translate directly to the hardware. How do I have bus protocols where the recipient turns on only when there's an exchange to happen? So the same issues show up in different form at each of those layers, and a lot of it is getting the alignment across them. And that's where some of these efforts at software synthesis that really can look all the way from hardware to application have this potential to really get each of those layers working together. Because that's what it takes to go to sleep. One little thing can keep you awake. You all know that. One little nagging thing keeps you awake all night. That's what happens for embedded devices too. Okay.
Well, thanks very much, David.
Thank you.